This week we will talk of ensemble methods. So let's get some basics on ensemble. There's what we call the no-free-lunch theorem, which is stating that if we are looking at all possible and every problems that we can think, even including problems where there is not a clear relation, a smooth relation between related points and their decision in terms of supervised learning, for example. If we take this into account and we integrate over all these possible problems, the no-free-lunch theorem states that there are no learning algorithms that are superior to the others for every problem. So this means that looking at every possible problems, nothing is better than says random decision or anything like that. So just to say that this is not really true in the sense that this is true in theory, but in practice, we have some kind of regularity, some kind of smoothness in the problem we are looking for. We are not looking at problems where just a small difference in the input leads us to something very, very different. It would mean that there are no relation, local relation, no local smoothness between instances. So of course, when we are facing such problem, anything we can do will lead to the same kind of, I would say, performance equivalent to a random decision. So we should take into account the fact that there are some irregularities, but I would say in general, if we get a problem, we've got a method that is really good for solving one given problem, it means that it is kind of specialized on that problem, and it is likely that this model will not be very good, will be in fact relatively poor on other types of problems. So the specialization implies being not really good in other cases that are somehow opposite to the current case. So there is a kind of trade-off to make between having being really good in some cases and having some capacity to work over, let's say, a broad range of problems. There are some statistical arguments toward the use of ensembles. The first is that basically, if we are averaging over a set of samples, this is much more reliable than relying on a single sample value. Even though maybe in some cases, we will get one sample that is pretty good, pretty well estimated of what should be done here or what is the right value. We may also be unlucky. We may also have a sample that is quite poor. So if we go with averaging, if we get many samples and we average, somehow their values, we will get something that is closer, that is more reliable than having only one sample on which we are relying on. And the point is that we are somehow eliminating the variance by averaging on an ensemble decisions. So it means that if we have many decisions, this variability may come from some cases that may make a different decision from the, I would say, the most common decision. And these, I would say, rare and different decisions are likely not to be good. Otherwise, it should be this decision that we should take in general. And such variance that we are observing over all possible decisions made by many models can be a problem. So by averaging, by making use of many models that we put together and for which we average decision, we also reduce the variance on the final decision that we'll get from them compared to one model decision. And as such, we are somehow removing the noise from individual classifier decisions, because some classifiers may be relatively good in general, but may in some cases made very noisy or just a bad decision, choose the wrong label, for example. And we can consider this as some kind of noise, but if we look at many of these models, we will be able to get rid of what we consider as decision noise in our models. This comes to the common, I would say, statement that several heads are better than one, in the sense that relying only on one judgment may not be the best thing to do. Especially when we are unsure, we may ask for several people, several experts or several people knowledgeable of a given situation to make a decision. And if we go with voting, we expect that voting may be better than single individuals that are making a decision. There is also this idea of error correcting output codes. So that means that we can design somehow methods that are based on these notions of having validation codes and correcting codes in the message. This refer to numerical digital communication, where we have a channel, we send bits, and we may send more bits than required to encode the message, because we have some extra bits that would just first maybe validate whether or not we have some corruption in the message. But the output correction codes are in fact bigger check values, checksums somehow, that allow to fix if we only have 1 or 2 bits that have been corrupted, because there is some redundancy that allow us to validate what should be the right code, the right message that is sent with some number of bits. And so over these voting methods, these error correcting output codes, we can also look at approaches in machine learning where we will dynamically sample data or features. So the point is to say, let's not use the full data set, let's not use the full set of features, let's use a subset of these. Let's build models on these subsets, and let's assume that this will make, I would say, different members that will not make the same decisions, will not make the same mistakes, such that as an ensemble, they will get us with better results. And we are also the mixture of experts approach that we will see this week in a sense of having specialized models, experts on specific aspect of the problem. So every expert is expert on something different. There might be some overlap, but basically their expertise should be varied. And from that the varied expertise, we can gate and gear, like a given sample, we assign this to that expert because this sample belongs to the field of expertise of a given member. In fact, if we go into more philosophical, I would say fundamental idea, is let's go with the notion of justice and the notion of judging someone with a jury. So not having one judge, but having many people that are evaluating whether or not someone is guilty of something. The point is to say, okay, if we try to do some maths over that, what will be the probability that a given jury will get a majority decision right? I would say we are in a situation, we have the right decision, the correct decision, we have the wrong decision. So let's say that the right decision is not guilty, for example, for someone who was accused of a crime, and the wrong decision is to say that this person is guilty of that. So if we assume that every jury member, so every person on the jury has a probability P of making the right decision, of saying not guilty, and we assume that if that probability per jury is more than 1/2, so it's, I would say they have 2 decisions, and they are more likely to choose the right decision than the wrong decision. The average decision over the full jury through voting will tend to 0 with a large number of participants. That means that we will choose the right decision if we vote over enough jury members. The chances of not picking the right thing is getting close to 0. Conversely, if the probability of choosing the correct decision is less than 0.5, the probability of the jury will reduce towards 0. Basically, the jury will take the wrong decision as they get enough jury members will get a good confidence on that. The trick here is that the votes are deemed to be independent and identically distributed. So they are said IID. That means that if one jury member is selecting the wrong decision, the chances of the other jury members of picking up the wrong decision is not more than if it has taken the right decision. So they are independent, so they will not make the same mistakes at the same place. They will not pick up the wrong or the right decision in the same way. Every jury member is independent And it will, I would say, can have a really relatively low probability of picking up the correct decision, can be like 60, 75% chances of picking up the correct decision. But if they are picking up the correct decision independently of the others, and if we are averaging or voting over a large number of members, we will reach the right decision. So this RID hypothesis is kind of strong, in fact, really strong, because we know that especially when they are human in the factor, that are a factor of this, they can be influenced, they can rely on the same kind of assumptions or measurements. So the independence hypothesis is kind of strong. So this idea, this what we call Condorcet's jury theorem, has been proposed by the Marquis de Condorcet in 1785. He was a kind of mathematician slash philosopher in France during the French Revolution and before. So he was proposing somehow some kind of mathematical justification of democracy, because basically democracy is getting everyone to vote, to pick up the right, or what's it, to pick up the person who should be in charge. So we assume that if we simplify the problem of democracy to this kind of correct or wrong decision through many people who are voting, we can get to that theorem that demonstrates that this is a good approach to pick up the right decision. And this theorem has been studied in political science. So it goes beyond that course, but it's kind of justification of basing, of using ensembles somehow by picking up machine learning models that are making the same decision over a given, making independent decisions over the same samples, and see that we are taking these multiple outputs to make the final ensemble decision from that. So the point is to create this ensemble. So we want to create models put in as an ensemble that will achieve good results, that will be independent from each other. So there are some different learning algorithms that are different approaches that can be used to create this ensemble. The first one may be to use different learning algorithms. We can say, okay, let's build up an ensemble with a SVM, with a multi-layer perceptron, with a k-nearest neighbor classifier, and so on. So the idea is that these different learning algorithms are not learning the same way. They are not providing the same kind of results. So the assumption about the data, the bias, the variance are different. Another approach may be to rely on different hyperparameters. So maybe if we are dealing with neural networks, we can train different topologies of neural networks, different number of hidden neurons, different number of layers. We can assume that varying this will lead to different models, so they are likely to be diverse. Another approach with the k-nearest neighbor is to vary the number of neighbors, vary the type of coherence matrix in parametric methods. The point is to change the hyperparameters to get different models. Another view is to change the representation, basically what kind of measurements, sensors, features, basically that we are taking to make the learning. So using different features, so making use of feature subsets that are different from one member to another is a common approach for that. It is used for random forest, for example, random subspaces. So these approaches, these ensemble approaches, are relying on the training, getting models that are trained on different feature subsets. We can also pick up different training sets. This is what is used, for example, with bagging, where we will simply randomly sample data with different probabilities over each. No, at first, bagging is with the same probability. So it's basically just randomly sampling different subset of the training set and training a model on that. And hopefully, with these different training sets, the model will be slightly different from each other. Another approach will be like what we do with boosting, for example, to sample according to the misclassified data. And over the training, we will train one model at a time. We will increase the sampling probability for the R data, the data that tend to be misclassified, versus reducing the sampling probability of the easy data, the ones that are always, most of the time, correctly classified by the models. So the point with these approaches is that the basic classifiers, the members of our ensembles, don't have to be very precise individually. We are not looking to get super strong individual models. The point is that we are looking at a good ensemble, which can be built from many simple basic classifiers. And in such case, given that we may get dozens, hundreds of models, if we wish, we need to target some kind of simplicity. So in fact, simplicity is better than performance. And I would say for a given budget in terms of memory and capacity of computing, it's probably better to get a model that is 10 times faster, 10 times smaller, and getting 10 times more of these members versus getting 10 times less compared to the simple models of complex classifiers that are really well performing. So simplicity here is not, I would not say always, but it's often better, much better than performance. And the point is to reach some kind of diversity in the classification. So we want them to be specialized. We want them to be diverse. We want them not to make the same mistakes on the same sample. We want, if they are independent, they will make different mistakes at different samples. So on average, through voting, we will be able to be robust to the individual classifier mistakes. And we can just simply demonstrate that if the classifier errors are ID, basically with a number of members that are reaching infinity, or any kind of really large number of members in our ensemble, the ensemble error will reach the optimal base decision rate. So it will be as good as having a perfect modeling of the distribution of the distribution, so such that the decision will be the optimal ones. Even though it's not at 0% error, they will be at the rate that we cannot get any better in terms of generalization. So some approaches for combining these decisions, we can do some kind of parallel combinations. So the idea is to have multiple experts that can be the same or can be different, like through voting. When you are voting, every members is voting, every decision is made independently, and then we pick up the decision that has received the most votes. Mixture of experts is similar, except that we are somehow weighting every member according to its expertise. So a member that is highly expert for one sample will get a much higher weight, but you know the expertise is computed in parallel with each member decision, or even stack generalization, which is another example that is not that far from mixture of experts. We can also have some serial models. So we have multi-stage combinations. What we say, we just go at the next stage classifier only when we are in doubts, only when the accuracy and the confidence on the decision is too low, is below a given threshold. So if we formalize ensemble methods, we can see this as basically a meta model. So we have this function h bar here, which is basically the age of the ensemble, the meta classifier view of that ensemble. And we have a function f that is the combination function that is acting on every member's output, every member's decision. So h1x, h2x are, for example, the application of member 1, classifier 1 on the x data. We get the decision from the application of function h, and likewise for the L up to the Lth model here. And we have some parameterization here that are corresponding to the combination parameterization.